Alright, welcome back. What we're going to be doing today is learning how not to use the limit definition of the derivative. We're actually going to be learning how to cheat at taking the derivative. So while the limit definition of the derivative is very useful, because it does allow us to actually compute the derivative for many functions, the calculations are kind of boring, a little tedious, and you've probably noticed as you do some of them, highly repetitive. For example, taking the derivative of f of x equals x and taking the derivative of f of x equals 3x, you almost do exactly the same calculation. And if you were to take the derivative of x squared or 5x squared, again, you'd almost be doing exactly the same calculation. And since a lot of these have incredibly similar calculations and recognizable patterns, it would help us if we could actually not have to use the limit definition each time and just use the recognizable patterns to take the derivatives. So ultimately, the purpose of mathematics, and the reason why most of us do math, is it allows us to ultimately cheat. Allowable cheating is the development of new methods for solving old problems. Often this requires a one-time upfront investment in exchange for great long-term gains. So whenever we come up with new rules, usually there's a lot of work just to get the rule, but once you have it, it all of a sudden will simplify all of the calculations you had done before by a vast amount. So here are a couple of rules. 1. The derivative of a constant is 0 for all constants. Why? Well, let's let f of x be a constant and write out the definition of f prime of x. Well, that's just the limit as h goes to 0 of f of x plus h minus f of x over h. And since f of everything is the constant c, we just get the limit as h goes to 0 of c minus c over h, which is the limit as h goes to 0 of 0 over h. Well, as long as h isn't 0, that function is 0. And so the limit of 0 is just 0. And so from that we can see that the derivative of all constants is 0. Well, that wasn't so bad. Let's do another. The derivative of the function f of x equals x is 1. Well, looking at f of x equals x, f prime of x is just the limit of f of x plus h minus f of x over h as h goes to 0. Again, we can just plug in x plus h and x for our function. Here we get x plus h and x respectively. And so this is the limit as h goes to 0 of x plus h minus x all over h. Those x's cancel, and we get the limit as h goes to 0 of h over h, and as long as h isn't 0, h over h is just 1. And so our limit winds up being 1. So here's a slightly more complicated one. The derivative of a constant times a function is the constant times the derivative of the function. So what we're going to do is we're not going to work with the constant times the derivative of the function in the beginning. We're going to create another function, g of x, which equals c times f of x. And we're going to take the derivative of that. And the derivative of that is just the limit as h goes to 0 of g of x plus h minus g of x, all divided by h. And if you try to plug in x plus h to g of x, you get the constant times f of x plus h. And so this looks like the limit as h goes to 0 of the constant times f of x plus h minus the constant times f of x, all divided by h. Since both of those have a constant in common, we can pull it out. That looks like this. And we have a rule about limits. The limit of a constant times anything is the constant times the limit. And so that c can actually be pulled out front. And so when we do, you should notice that we have c times this limit, And the limit looks exactly like the derivative of f. And so it is. And so we write that the derivative of g of x is c times the derivative of f of x, and all g of x was c times f of x. And so our rule is true. One more rule, we have the derivative of the sum of two functions is the sum of the derivatives. So let's come up with a new function. We're going to call it k of x, and it's going to be the sum of f of x and g of x. Well, then k prime of x is the limit as h goes to 0 of k of x plus h minus k of x over h. Well, if you plug in x plus h to k of x, that's f of x plus h plus g of x plus h. And so we get this expression here in our limit. And if we rearrange it and move f of x next to f of x and g of x next to g of x, we get f of x plus h minus f of x plus g of x plus h minus g of x. And then we can break this up into the following two limits. And each of those is a derivative. The one on the left is the derivative of f of x, and the one on the right is the derivative of g of x. And so we get f prime of x plus g prime of x. We were able to do this because we know that the limit of the sum of two functions is the sum of the limits as long as both of them exist. Alright, here's a tricky one. The derivative of x to the n is nx to the n minus 1. This one's incredibly important, and you're going to use it, I would say, almost as much as anything you would use in the entire course. It's so important that it has a name. It's called the power rule. And as to proving it, you're just going to have to trust me for now. We'll prove it in the future when we talk about taking the derivatives of logarithmic functions. But again, for now, you're just going to use it. So let's go ahead and do an example using the rules. So look at the function f of x equals 3x squared plus 5 radical x. We're going to go ahead and take the derivative of this without even using the limit definition. So the derivative of this function, well, the first thing you notice is that we have the sum of two functions. So the derivative of 3x squared plus 5 radical x is the derivative of 3x squared plus the derivative of 5 radical x. Now both of these have a constant times a function. And so what we're able to do is we're able to pull out the constant from the derivative. So we just have 3 times the derivative of x squared plus 5 times the derivative of x to the half. Now I've replaced the radical with x to the half because now we're able to use the power rule rather than having to think about it in terms of anything else. The power rule says that the derivative of what's inside the first set of parentheses, which is x squared, is 2 times x to the 2 minus 1. And the power rule says the derivative of x to the half is 1/2 x to the 1/2 minus 1. 2 minus 1 is 1, and 3 times 2 is 6, so 3 times 2 to the 3 times 2x to the 2 minus 1 is just 6x. 5 times 1/2 is 5 halves, and x to the 1/2 minus 1 is x to the negative 1/2, since 1/2 minus 1 is negative 1/2. And we can go ahead and pull the x to the negative 1/2 into the denominator to make the power positive, and we get 6x plus 5 over 2x to the half. And going one step backwards, since x to the half is the square root of x, we can nicely write this as 6x plus 5 over 2 radical x. So go ahead, use these rules to take the derivatives in the homework, and I will talk to you again soon.